This is the solution for Evans Chapter 5, Problem 16. The problem reads, using the data in the Excel file, Consumer Transportation Survey, develop a contingency table for gender and vehicle driven, then convert this table into probabilities. So now as we're reading this in the book, we should be jumping to the pivot tables. Okay, so when we're talking about contingency tables, we want to show major headings and rows, and then we want to show the subsets along columns. Okay, and that's what we can do with a pivot table here. Okay, so we're going to have to go retrieve our data, and I have that file teed up right now. I need to go over there and grab our data from their file that they tell us about. So I'm going to go over to Consumer Transportation Survey information here, and I am going to grab just part of this because everything from column E to the right is only used for some other problems, I suppose. It's not used for this one. So I'm coming in and grabbing the first bunch of columns here, Control C, come back over to my empty file, and I insert that in there, and you can see that it has vehicle driven, the type. Actually, we're not even going to use that, and actually, we don't even use columns B or C, so I'm just going to delete those out of here. Let's not be confused. This is how simple it is. We just want to know what kind of vehicle is driven by whom, male or female. Okay, so we want to grab our data, do a Control A here, and it should grab the data there, and we're going to insert a pivot table. Insert pivot table. And we're going to use our existing worksheet. It wants to know where we want to do this, where we want to drop that, and I'm going to drop it in right here. Okay. Okay, so we'll be able to drop that in there. Now we need to set it up. Now in this problem, there's 4 different concepts that we're testing out in here. This is why I'm using problem 16. We're using some gross or top level or simple statistics on this. We're using the unions. That means when A or B, we want to know when A or B, what's the probability. That's a union. We add those things together in general. And then we want intersections, which are, it's an and function. We want to know when something's this and that. So it becomes even a tighter subset. And finally, we want to show the dependent variables, A given B. Okay, so you're going to see some of everything that we just mentioned here down in our problem set here. So I just wanted to show that. I'm going to move these out of the way a little bit so that not in our way as we're going forward. Okay, so we come back over to the pivot table here. What does it want? It wants to know gender versus vehicle driven. So gender will usually be the row labels and or the Y dimension as it goes down. So we're going to drop our gender down here into the row labels. And we wanted to look at what kind of, per gender, what kind of vehicles driven. But remember, that's just going to give us something simple. See, this is very, very coarse here. And the way that we can parse this out when they talk about contingency is we also want to put the vehicle driven in column labels. So we want to parse it out. We want to separate out other values here. Okay, we want to separate the sub-values of everything going on. You'll observe something here. There's a cell that has nothing in there. It should be 0. It should behave as a 0 whenever we need it. Okay, so something I'll do is I'll just go in here. I want to center up these numbers so they're more readable. So they're sitting underneath. Well, we might as well do the same here, right? We'll center our column labels too, so now everything's sitting underneath where it should be. Okay. So we'll get, we need an A, a B part, a C part, a D part, an E part, an F part, and then G gets a little bit intricate. So I might break that out as a separate file, separate video. Okay. So the first thing we want to know is what's the probability that a respondent is female. So these are some of the gross numbers, the type of top level numbers that we have. So it's getting us warmed up. So the condition here that we're trying to figure the probability out for, and it will be just simply female. Okay, so is it a female? In this column, we'll put in our probabilities. Okay, so how will we get that? You just come up here and we can look at total score over here. So female, this is going to equal that number, the number of females, over the total population. There, it's 50, and we should have 58% chance if we randomly look in the table that we're going to find a female. 58% of the time a female comes up if we're doing this randomly. Just want to format those numbers just a little bit. Go in there, do number, and 4 places. I think usually looks better. Okay. The second condition that we're looking for is the probability that the respondent drives an SUV. Okay, so we can come in here, and again, this is a gross high-level number. Okay, so we can just come in here. We're looking at tabulations. It's tabulating over to the right, tabulates down to the bottom. So we could just take a look at SUV, and the probability that it's an SUV is just simply going to be the number of SUVs here over the total number here, and that is equal to 30%. Okay, so the next thing that we're looking for is what is the probability that a respondent is male and drives a minivan. So we're looking for the probability male and minivan, the manly minivan. Okay. So what is that probability? Well, one thing we can do, I'm going to move the questions aside just a sec here, and use these drawings. These drawings illustrate a little bit about what's going on there. So we're looking in the total population here. We have male and female and all these other subsets in here. And we want to know male and minivan. Okay? So let's say if we look up here, we're going to see the number of males is 21, and the number of total minivans is 9. So I like to just usually make these ellipses relative in size. So there's more males than there are SUVs. I just try to make them a little realistic so they reflect relative sizes here. So in our total set, we have 21 males. It's 21 males up here, and we have a total of 9 minivans there. Okay. So what we're looking for is the overlap here. So probability of male and minivan is going to equal, of males, we have 1 minivan there. So the intersection, we're looking at the intersection of minivan and male. We can visually see the intersection up here. There is only 1. It's telling us that's 1. So it's going to be equal to that event over the total number of events. So we just knocked off a couple of our list of different kinds of things. We looked at some of the gross numbers that are up there, and now we're looking at, that was an intersection of 2 things. Okay. So now D, question D, what is the probability that a female respondent drives either a truck or an SUV? Now we have both union and intersection in here. So we're looking for the probability of female and truck or SUV. Okay. So in words, that's what we're looking for. And so what we can look up here is this intersection. And so we're looking at the intersections of SUV and female, which would be 5, and the intersection of truck and female, which is 0. So it simplified the case just a bit. So this is going to, the probability is going to end up equaling 5 over the total number of records that we have here. So you have a 10% chance of having a female in a truck or an SUV. Okay, so with E, when we take a look at E, E says if it is known that an individual drives a car. Now we're getting to conditional probability here. Okay, if it is known that an individual drives a car, given a car, what is the probability that the individual is female? So we're looking for the probability of female given to car. Okay. Now the probability for that is equal to, so that probability is going to equal to the probability of female and car over probability of car. That's the equation. Okay. All right. So we'll figure this out. There's a long way, there's an easy way, and there's a hard way. But we're going to do the hard way first. It's just a little bit more complicated. Just putting in more information than you absolutely need. But it's probably the safest way. It's the long. Let's put it this way. It's the longhand version of it. Okay. So the probability is going to equal something over something. So the first thing is the probability of a female and a car. So that probability is going to equal, we're going to have something over something. Put our parens in to get started with here. Probability of a female and a car. Female and car intersection is 16. The entire probability the entire probability is 16 over 50. Okay, so that's the probability of a female driving a car, and we need that over the probability that it's a car. Probability that it's a car is a total of 22 over the total set, and we got to divide by 0 there. I'm going to do this again, so it's just equal to the probability of female and car so it's probability. So we need the probability of a female. So we need the probability of a female and a car over the probability of a car. That's the definition of conditional probability. What it's basically saying is that once we know one thing happens and that there's an intersection of two different things happening, given B, in this case, given B, what's the probability of A? Well, we know we can look at where A and B happen here, and the probability is just going to be that the probability will be the intersection of that over B. That's what this equation means. The probability of F, the female in car, is this over the probability of car. Okay, so it changes your probability a bit. Okay, so now we'll calculate it out. All right, so it's equal to the probability of female in car is 16. Here's that intersection here. So it's going to be 16 over 50 over the probability of a car. If we look at the sum of a car, here's the probability of a car is 22 over 50. And our probability is 72, round up to 73%. Okay, so that's as simple as it is. And visually, that's what you have to look at: is given B happened, and A intercepts or intersects B. Now we know that everything has to lie within B. Just this area over the area of B is what we just figured out. Okay. So problem F: if it is known that an individual is male, so given male, what is the probability they drive an SUV? So this is the prob of SUV given male. Okay, that's what we're looking for. So that's going to be probability over here. Let me move this just a tad. It's going to be the probability of SUV and male over the probability of male. That's we have to figure out a couple things here. So I always like to have these drawings around because then you can just look at your chart and figure out what the intercepts are here that you need to know. Okay, so the probability SUV and male would be SUV and male, the intercept there. So the probability is going to equal 10 over 50 over the probability of male, which is 21 over 50. Okay, we've got to fix that. I left the paren out. Let me put the paren in here. There we go. Now the probability is, again, if we take a look at the equation, I did 10 over 50 over 21 over 50. That's the probability of SUV and male divided by the probability of male. That's what we just calculated there. So the probability is 47, round up 48%. Okay, that given that it's a male, it's probably that there's an SUV. Okay. And I'm going to take G into a different video, add them together. This is a continuation of problem 16 in Evans chapter 5. And part G says, determine whether the random variables gender and the event vehicle driven are statistically independent. What would this mean for advertisers? So what I've done is I've just copied down the numbers from our pivot table here. I did it by hand. I just entered them in by punching the numbers in here, adding all the column and row labels on here, and then summing them up. I summed all these numbers up. So this is just a reproduction of the pivot table above. Then what I did is I created a table of the probabilities of any one of the joint probabilities here. So when we have a joint probability of a car driven by a female or owned by a female here, these are the joint probabilities, the joining of the car and the gender, car and male, car and female, minivan female. So these are the joint probabilities, okay? When we sum these up, these are mutually exclusive. Now we're going to end up looking for dependencies is different than exclusivity, okay? Exclusivity says, is there any overlap between any of these joint probabilities here? And what we do is we add in our marginal probabilities. We sum up the columns down at the bottom of the columns. We put in a sum here. End of the rows, we put in a sum. These are the marginal probabilities that are interesting later on when we're looking for dependence. Not exclusivity, but dependence. Two different things. Okay? And basically we want to say is in the overall general population, ownership of a car influenced by whether we're dealing with a female or a male. Okay? When we look for independence, we use this rule up here. The probability of A given B is equal to the probability of A. That means the fact that we are at the conditional probability of it, say, being a female. Okay, what's the probability of a car given that you have a female? Okay, what's the probability of that? Does that actually just equal the probability of having a car? So does it change when we have the probability of having the fact that we have a female owning that? Okay, and so we're using this for marketing information. We want to see where these dependencies are. So we're looking for patterns here that could end up being a lot of decisions can be made from that information. Okay, so again, this is just the probability table here, and this is just the straight up numbers that we had from the pivot table out of the original data. Okay, so a couple of things here. I created a couple helps. So one of the things is when we move in my diagram here, you'll see that I pointed arrows to where the marginal probabilities are. Okay, so these marginal probabilities are shown by arrows. Okay, there's these at the end of the row and these at the end of the column. Those are marginal. The ones in here are joint. Okay, now what I'll do is just to indicate that is these are our joint. This helps out a little bit, I think. And I put a label over here. So the joint probabilities are shown inside the blue box here. Okay, just to be clear. Now, what we're going to do is we want to see the conditional. Remember, we want to see the conditional probabilities of, for instance, given that there's a female owner, what the probability of a car is. And now that we have the joint and marginal probabilities in there, we have almost everything we need to compute this. So what I did is I created a conditional probability table from what we have up here. Okay, it's laid out the same way. The column headings are the same. The row headings are the same here. But I'm using the equation for the probability, the conditional probability. That means the probability of a car, given that it's a female, is the joint probability that's car and female, over the probability that it's a female. So that's the equation we've used in earlier problems over there. And so here in this, when we want to look at the conditional probability, this is the equation right here. So we have the joint probability was E35 in here, and we divide by the marginal I35, which is here, which is just the female entries in the table. Okay, and so I calculated all of these out. What I'll do, help our eyes just a bit, is I'll put another box around these. Okay. So now when you see a grand total of a row, it's equal to 1. This is where our world is reduced. This is where we're saying that we know that we have a female driver. What is the probability that they drive a car? And we're using just the intersection space here over the area of the fact that this is we're looking at a female, the female population here. Okay, so we figured all these out. Well, what happens is that now that we have the joint, the probability of A at all, we even have the marginal. So the probability that one of our entries has a car is 44%. So that's the probability of owning a car is 44. Does that equal the probability of it's a car given a woman? And when we come down here, it certainly does not. it's more likely that a woman is driving it. You can see down here the conditional probability is higher that a female will be driving it. Once you know that there's a female driving it, it's more likely than the greater population. It's more likely here that a female driver drives a car. That's how we interpret this. We'll go over this in class, and we'll get into these interpretations a little bit more. Hopefully you found this video a little bit helpful, but as I said, we'll review it in class.